I'm going to give you now an overview of Quail modeling, which is specializing on computer modeling of materials, molecules, and their environment. Today's research and development in material science and chemistry is mainly experimental. The reason for that is very simple. All those computational tools we have today, they are comparably blunt when it's about reliability and predictive power, for the simple reason they are not able to include the environment. And they can't do that due to a very high numerical load. So this is what Quail modeling enables. We are very efficiently building on top of those tools already, or the available infrastructure, but we allow for millions of atoms to be included. And of course, that gives us a very sharp spearhead to find new drugs, emulsions, catalysts, new materials, whatever you desire. As I mentioned, most of chemical research is experimental. Well, for pharmaceutical industry, that's about 95%. Well, the result of that is a very, very expensive way for drug molecules to the market. It is taking way too long. And in my eyes, the simple reason for that is experiments tell you what happens, but only computer models tell you the why. Here is an example what difference it makes to include the environment in the prediction of chemical reactions. So together with experimentalists at Purdue Chemistry Department, we've looked at specific chemical reactions in the case of droplet-gas interfaces. And we found an acceleration of about 10,000 compared to the bulk reactions. This is actually in quantitative agreement with experimental observation. So you see, it's critical to include the environment. And we expect the same to happen when we look at the formation of DNA molecules at droplet interfaces, cloud formation, which involves solid aerosols, solid gas and liquid interfaces. Well, we are excited to look forward to those calculations. In the area of material science, Quail has proven to be critical as well. So there is a common misconception that alloying graphene with silicon would open a band gap. There is controversial experimental data. It rather shows only a shift in the band structure instead of a band gap. And indeed, that's what we see when we apply Quail on that system. Instead of applying the idealized assumption of periodic silicon distribution, when we assume a random distribution, we get indeed just a shift that happens to be quantitatively agreeing with the experimental measurements. So with that, and of course more results, we are confident we will be able to reduce the required amount of experiments by 50% in R&D of chemistry as well as material science. Getting back to the drugs, well, I hope it's clear that drug molecules run through very different environments, starting from the formation into pills, then when you swallow that, and depending on your metabolism, it is known drug molecules behave differently. With Quail, we are confident we will predict that accurately. Compared to state-of-the-art technologies like density functional theory and molecular dynamics, well, both methods are either fast or accurate. When we put them in conjunction with Quail, we have seen we can be fast and accurate at the same time and have a very, very high predictive value. The markets we are currently looking at, well, we are focusing at the moment on prediction of drug molecules due to the high commercial impact we see there. So we believe we can save about $250 million on average for in the process of finding new drugs. Of course, there's many other exciting markets in the chemistry industry. Apart from that, we want to look at biotech and food and feed, and of course also material market. In all of those, we expect we can reduce the amount of experiments by 50%. We have filed a patent and copyright protection. We are currently developing a first product. Of course, we are heavily publishing at the moment. We require support to hire professional software developers. We have to convert the academic Quail technology into a commercial tool. We are currently working with a potential customer on customizing the tool towards the required data and usage format and the speed. And we hope to acquire that customer, the potential customer, soon as an actual customer. Thank you very much for your attention.
My name is Dr. Ray Barretto from Purdue University Northwest in Westville, Indiana. The technology I would like to talk to you today about is the photoreactor, which we have developed for the remediation of organic materials and pharmaceuticals in water. Organic materials such as organic solvents, metabolic disruptors, and pharmaceuticals and narcotics can find their way into the water supply through a number of point and non-point sources. Once they have made their way into the water supply, they find that these compounds tend to be very difficult to remediate and to remove from the water through traditional treatment sources. However, it has been found that a number of these compounds are susceptible to photocatalytic degradation using titanium dioxide and oxygen. In our lab, using these techniques, where we take the substrate material and apply titanium dioxide and oxygen to the system, we're able to develop a photoreactor utilizing titanium dioxide that has been suspended onto glass beads that have been put into a glass tube. The substrate material is then circulated through these tubes, where it is energized by fluorescent lights from an external light source. Using this system, we were able to patent our photoreactor through the Purdue Research Foundation and the Office of Technical Commercialization. We found that our photoreactor was able to convert a significant amount of the substrate being added in a very reasonable amount of time. Using our system, by varying the flow rate and the volume of material, we're able to determine that our photoreactor was capable of destroying up to 1 part per million, 1 milligram per liter of substrate. Through the course of doing our investigation, we're able to determine that the process was catalyst limiting, indicating that as the substrate concentration goes down to a level more consistent with that observed in a contamination stream, the ability to convert the substrate material is going to increase. Through our investigation, we were able to determine that a number of organic materials, analgesics and pharmaceuticals, and antibiotics and stimulants were susceptible to photocatalytic degradation. Using our process, we have decided to expand our research to now include a number of new pharmaceutical compounds and organic materials. Of particular interest to us are firefighting foams, such as polyfluorooctanoic acid and polyfluorooctanoic sulfate, as these compounds have proven to be particularly difficult to treat and address using any conventional means. We also have been trying to redesign the reactor, so that we are now going to be utilizing an internal light source instead of the external light source that we originally patented. In this new photoreactor, we have the titanium dioxide coated onto glass tubes that have had the internal light source inserted inside. Using this system, we're able to design a new photoreactor that is both compact and much more commercially viable. This is a process that we have developed, and this is what I'd like to present to you. Thank you very much for your time.